In today's lecture, what we're going to do is apply some of the ideas we developed in the previous lectures to understand the properties, particularly the atmospheres, of Mercury and Venus. This lecture will have 4 parts. We're going to begin by talking about Mercury, then step back a bit and talk about magnetic fields, what they are, and that's of interest because Mercury has a magnetic field that's actually a scaled-down version of Earth's magnetic field, and we believe that magnetic fields play an important role in the evolution of a planet's atmosphere and potentially in determining whether a planet is habitable or not. Then we'll begin with the first of our interviews. What we're going to do is I'm going to sit down and we'll talk with Sean Solomon, the leader of NASA's MESSENGER mission, which is currently exploring the properties of Mercury. It's currently orbiting around the Sun and Mercury. And then the final section will turn to Venus. Venus is sort of Earth gone bad, and we'll talk about why that happened. So let's begin by talking about Mercury. Mercury, of course, is the innermost planet of the solar system. It moves on quite an elliptical orbit. The Earth's orbit is close to circular. The difference between the minimum distance from the Sun and the maximum distance is quite small. In the case of Mercury, the difference is pretty large. Its closest distance is about 0.31 astronomical units. At the furthest distance, it's 0.47. As a result of this large variation in the case of Mercury, the flux from the Sun hitting Mercury varies by nearly a factor 2. Well, I've drawn Mercury's orbit as an ellipse, and it would be if Newton was right about gravity. Mercury's orbit slowly precesses. The ellipse slowly moves around. And this precession, which was first seen characterized in the late 19th century, is one of the things that led Einstein to his theory of general relativity. And one of the successes of the theory of general relativity is that it explains Mercury's precession. Mercury has a number of interesting properties. The Earth rotates very quickly. We have 365 or 365 and a quarter days per year. Every 24 hours, we see the sun rise, the sun set. If you lived on Mercury, life would be very different. Mercury rotates really slowly. It orbits the sun every 88 Earth days, and for every 2 orbits around the sun, Mercury spins around 3 times. If you were sitting on Mercury's surface, because as you spin, you move around the orbit, you'd find that it takes 2 full orbits for 1 day. You would have, as a Mercurian, a sunrise every 2 years. As we'll see, this has a big impact on Mercury's climate. You're exposed to the sun for a continuous year, and then you have another year living in shadow. We remember we talked about properties of planets and planetary temperature, and what we did in our estimates of planetary temperature was we balanced the energy that hit the planet's surface with the energy that radiated. This was the flux that hit the planet's surface. This term included the effect that some of it bounced off. You'll notice that the flux that hits the surface depends on the flux coming in from the sun times the area of the planet, because what we're assuming here is all the energy that hits the planet is distributed around the planet and then radiated in all directions. And we balanced these two and got this equation that describes the temperature of a planet without an atmosphere. Now, that's not a very good approximation for Mercury, because in the case of Mercury, there's no atmosphere, there's very inefficient heat transport. The energy that strikes one part of Mercury takes a very long time to flow to the other side. There's not efficient radiation, conduction, or without an atmosphere, convection moving that heat energy around. So in the case of Mercury, a better approximation is an instantaneous balance. That if you're, say, on the equator of Mercury facing the sun, the energy that comes in from the sun is balanced with the energy that goes out. And the balance is just between the flux hitting the surface, coming in from the sun bounces right back, and the thermal energy radiated. So this term here is our black body radiation rate. Here's the dilution due to the fact that the sun doesn't fill the full sky. And this is balanced. We can now solve for the planet temperature, and we find this equation here. And you'll notice there's no factor 2 here, that the temperature is about 40% higher because you're just in local balance. And this temperature is going to vary a lot during the day. If you think about what it's like to be on Mercury's surface, let's imagine ourselves on the equator, as the Mercury rotates, only a fraction of the sunlight starts hitting the surface. Showing this effect here, when we're on the equator at noon, all the light comes in, strikes the surface. As we approach dawn and dusk, you can see at dusk, there's almost no sunlight hitting. And the amount of sunlight that hits the surface is reduced by the sine of the angle. As a result, when we balance the flux instantaneously in with the flux out to solve for the planet temperature is reduced as a function of angle. We can look at it this way. If we balance the flux coming in, here's the flux coming in during the day, maximum at Mercury's noon, and then falls to 0. There's no energy coming in from the sun to the backside, then peaking again. If we do that to find the temperature, there are a couple different solutions, and the solutions will depend on the properties of the planet. If we're in the limit of instantaneous heating and cooling, we'll balance the temp energy in with the energy out, and we'd have a planet that heats up quickly, stays hot during the sun time, during the daytime, and during nighttime, it's quite cold. Heats up again during the daytime. That's a good description of Mercury. And at some level, it's a good description of being out in the desert. Those of you who've been out in the desert know that it can get very hot in the daytime, but also very cold at night. That's because it doesn't take that much energy to heat up that land surface. On the other hand, if you're on a planet with a lot of ocean, or say you're living in Hawaii, it takes a lot of energy to heat up ocean water, so that the temperature averages out. And what the planet's temperature is set at, it's nearly a constant through the entire day. So this is the limit in which we get to average over the whole day and just balance the total energy that comes in during the whole day with the energy radiated. In most places on Earth, we're in between these two cases. Energy comes in during the day, the planet starts to heat up. The peak temperature in most places is reached not at noon, but often around 3 or 4 o'clock, after you've had this big flux of energy in from the sun. As the sun sets, it starts to cool and continues to cool, reaching the minimum temperature usually just around sunrise. And that's the cycle that we experience on most of the Earth. But Mercury looks quite close to this case. In fact, if you lived on the equator of Mercury, you'd find that your temperature varies from 100 degrees Kelvin, right? So that's minus 173 degrees centigrade, up to 700 degrees Kelvin. So you would undergo in your Mercurian day, which does last a while, enormous variations in temperature. And these temperatures are amplified by the fact that you've got these elliptical orbit where the flux hitting the planet, even when the sun's directly overhead, varies by a factor of 50%. Mercury is an interesting planet in terms of its composition. It's a small planet. It's the smallest planet we have in the solar system. It's actually smaller than two of the large moons, Ganymede and Titan. In some ways, its properties not so dissimilar from Earth. Its density, about 5 grams per cubic centimeter, is quite close to the density of Earth. But its structure is quite different. It's got a very thick crust. It's got lots of iron that make it up. And it's composed of the materials, since it formed in the inner part of the solar system, which was quite hot, we think, when the solar system formed. It's made up of materials that have stay solid or liquid at very high temperatures. Materials like iron. Its surface, because it doesn't have water, records the history of bombardment, and, well, in detail quite different from the moon, a rough picture to have of Mercury's surface is a surface like the moon. And when we talk with Sean Solomon, we'll talk more about what Mercury looks like. One of the surprises with Mercury, and we can go back to applying our energy balance, is what was found at the poles. Like many surprises, in retrospect, it makes sense. The flux that hits Mercury depends on the angle the sun makes. At the equator, you get the full flux of the sun. But as you move towards the poles of Mercury, the flux coming from the sun starts to drop. A lot of the energy is spread out over a bigger surface as the sun is lower in the sky. As you get to the pole, very little energy reaches the pole. As a result, the temperatures of the poles are quite low, and a reasonable estimate of the polar temperature is about 180 degrees Kelvin, far below the freezing temperature of water. And in fact, this is an image from MESSENGER of Mercury, and what's shown in red are regions that contain significant amounts of ice. And you can see the entire pole, here's the North Polar region of Mercury, is covered with ice. There's about 10 to the 15 grams of ice at the pole of Mercury. One of the surprises we found when we got there. Now we're going to step back, think about applying some of these ideas that we've learned from Mercury to terrestrial planets. And I'd like you to think about what would the temperature of the equator be on Earth if we didn't have an atmosphere and if we were a planet whose property was like Mercury. Just literally take Mercury, move it out to the radius of Earth, and think about what its properties would be like. So why don't you think about that, and then we'll come back and talk some more.